Hey Mike, thanks for your question about what loop testers I was using in Baton Rouge, the class that we taught at Southwest Automated Security. I guess now it's last month, but just a few weeks ago. So real quick, I wanted to show you, I'm not 100% sure whether it was the inductance meter, so the LCR that I use, or whether it was actually one of the insulation testers that I use. So I thought it'd be a good opportunity to recap some of that stuff that I taught in class, because I probably go through it pretty quick. So I just maybe want to take a second and talk about those. So first of all, my go-to as far as testing inductance loops, and because it's just so easy to use. There's only one button, and if I'm talking to a guy on the other end of the line, I could say, do you make sure that you got ground hooked up to this, and make sure you got that hooked up to that. There's just two leads, and there's just one button, so it doesn't have multiple voltages. M500. And what's really interesting about this is that was designed to test insulation in AC motors, okay? So it puts out 500 volts DC, steps up 3 volts to 500 volts, and it's actually not exact 500. You can actually find that sometimes it produces more of that, and of course when the batteries are weak, it'll produce less than that. So when we're talking about insulation, what we're talking about in essence is the jacket of the wire. So here's some XLPE wire that's twisted together for a rig that I have down here, and you'll see it here in a second. I'm just going to be using the test inductor off of here. But so this is just XLPE wire, which is what we would just in essence call loop wire, but it's cross-link polyethylene, I believe, is what XLPE stands for, and most of your distributors will carry this, and you can buy it. It's not uncommon for you to be able to just buy it from even an online dealer that doesn't have anything to do with access control or automatic gates. So what we're talking about testing is the insulation, so the dielectric, the material that separates the outside world from the actual conductor itself. So this XLPE is the insulator, and sometimes called a dielectric. It depends on what we're talking about. Sometimes the jacket may be separate from the dielectric. Like if you're talking about a coax connector, sometimes they'll call the white material that's in between the jacket and the conductor a dielectric, and then they'll just call the jacket the jacket. But let's overall just say that we're talking about the insulation of the conductor. And what we want to do is we want to test if there's any cracks or breaks or anything in that insulation. And the way that we do that, similar to water pressure going down a hose with a leak in it, is we push as much force through it as we can. In this case, we're talking about electromotive force, okay? So we're talking about electrons getting pushed down the conductor and then seeing if it leaks out to ground. Let's go back to the water simulation. So when we're talking about water going down a hose, if you turn that valve on just a tad bit, you may not actually see water come out where the holes is. But if you go full blast on that valve and push as much water as you can pressure-wise through there, sometimes you'll actually see the leaks come out of the little pinhole breaks in the actual holes in the hose rather. And there are actually some hoses that are designed specifically to do that so they can water the lawn. You turn it all the way and it has a bunch of little pinholes down it. And this is a great test for any of your guys when you're explaining this. Get one of those soaker hoses or one of those hoses that water the lawns through those little holes, and turn it on just a little bit and see if any water comes out, and then turn it on full blast. So that's what we're doing with an insulation tester. What we're doing is we're taking 500 volts and sending it down that conductor so we can actually see if any of that voltage leaks, in this case to ground. Okay, so earth ground. Most of the time it's going to be through concrete. So what we're doing is we're taking ground and we're plugging it up to a good earth ground, generally the gate operator chassis, but that's not always the case, especially if you have a frame that has been painted and that's the only way that it's going into ground. That's not a good conductor, okay? As a matter of fact, that paint insulates the steel, or sometimes aluminum if you live in Florida, the steel from the actual earth ground. So it's not a good ground. And in that case, don't hesitate to drive a screwdriver or a piece of rebar in the ground a good 12 to 18 inches and throw the ground on that rebar that's going to earth ground. And then you'll actually take the hot lead and plug that into the one side of the loop. Now that loop is in a series, so if that other side of the loop is exposed, it's a possibility that you could get shocked. The other thing that you don't want to do is you don't want to leave it plugged into the control board, because most likely that circuit can't handle 500 to 900 volts, which this can put out. And then once we put that electricity to that conductor, we push a bunch of electrons through there. If there's a crack, it will leak out. Now, inherently in that is where a flaw can be in the test process itself and not give you the result that you want. So let's just say that you have a wire like this and it's going into a conduit into the ground. Once it hits the conduit, technically you can't see it. You can't see if it's broke, or you can't see if it actually does make a series, an actual loop, and then come back to the other side. You can't see it. So you don't want to assume that this actual conductor is connected to the rest of the loop that's actually in the ground. So there could be a flaw there when you're testing it. You test it, and in this case, what we're concerned with is we're concerned with the amount of resistance between the conductor and the material that surrounds the loop, if you will, that's on the outside of the insulation, typically concrete, blacktop, or dirt. You want to see what the difference is between those two, and what it's measured in is ohms. So ohms is the how we actually state how much resistance is in between there, the actual how we rate the physical property. So how much resistance is in between there. The higher the resistance, the better quality of the insulation in between the conductor and the material that surrounds the insulator. Again, in this case, concrete, blacktop, ground, earth ground. That is what we're looking for. We're looking at how much resistance is in between those, and the higher the better. Now, one thing that concerns me with using this tester is that you have bad, caution, and then let's just say all this gray area is good. That's not necessarily for the insulation and the conductors that we use for loops. However, it's a good guideline. Typically at 40 million ohms is where we say we're probably in the good category. Mike, what I think you were talking about, the tester that I had was this LCR. So this is the Agilent U1733C. Now, what we talked about is having a flaw in your test system when you're actually testing this. You can only be testing a small piece of wire because that's all you could see, but it actually could be cut underground. This meter would tell you that your insulation's good because maybe in that 18 inches, 2 feet, 3 feet, that it actually is still good, but it doesn't tell you whether your loop meets the other properties that the loop detector is testing, okay? And that's where your LCR comes in handy. It does probably the main property that your loop detector is actually measuring, and that's inductance. So LCR, these are the symbols that we use in the mathematic part of electronics engineering, L, C, and R. So C may be probably something that you guys are familiar with. I know R you definitely are familiar with. C is capacitance, R is resistance, but L is what we use to measure inductance, and we signify that in henries, probably because the guy who figured all this stuff out was last name, first name, Henry, or something along those lines. So that's where an LCR comes in. So when we're talking about most loop detectors, we're probably talking between 20 and 2,000 microhenries is where we want to take a look at. And if we're measuring, again, like I said, the fault that you could actually have in an insulation tester, only measuring a small amount, is that the inductance in this, if it's broken at both legs, it will have almost no inductance whatsoever, and it'll probably just read overload, as in it can't actually test anything on this. If you're measuring that small amount, it'll be easy to figure out. Now you can tell whether it's actually what your loop detector is looking for or not, and that's actually one of the reasons why you need to build you a test inductance loop as well too, and I'll show you that here in a second. But having an LCR will tell you whether you're in between those 20 or 2000 microhenries. The other thing that this can do for us is when we're testing motors or testing components on a circuit board, very, very accurate and higher resolution than probably your multimeter in capacitance and resistance. So actually what I would do when I connect this, and we'll do a little test here real quick, is I would just let, in this case, the multimeter figure it out, because it'll actually look through all of these properties and say, okay, this is probably what you're trying to measure. But let's take a look at this down here on a test inductance loops, and I'll show you what you mean. But it also has the ability to test resistance as well too, so you can actually test just a regular old circuit to see what the resistance is in between each one. As an example, if you're running power 100 feet away to a camera, you can actually twist it together at the end, put this on one leg, put this on the other leg back at the home run, and see what your resistance is, and you can calculate what your voltage drop would be to determine how much current that you need to put out at the voltage that's rated for the camera. So let's real quick take a look down here on the on this little tester that I got set up, and I'll show you what it looks like. So again, we've got 2 insulation testers. We showed this in class, and then we've got an LCR. The LCR is probably, Mike, what you were talking about. Measure the insulation testers. They're very simple. They send a bunch of voltage through the conductor to actually see if the insulation is good. So this is a test device. I won't go into the whole big deal of what it is, but it has a test coil on here. Basically, it's a dummy loop, okay? And you could check with EMX. EMX makes a dummy loop. I think BD Loops may make a dummy loop as well too. I think they make a couple of different testers. So first thing I'm gonna do is, if I'm out in the field, okay, we've got this much wire right here. It's actually through the going through the conduit down to the ground. Imagine that the loop right here is actually in concrete, and you can see that it's just one leg of a wire that goes all the way around this and then comes back out. And I have it tied into this, so that's why I have these solderless terminal connectors. So what we would do is we would most likely pull out our insulation testers. We probably wouldn't have a good lead that we could hook up to like this. You probably actually have the male, or in this case female, part of this plug connected into the control board. And if you do, you can actually just pull it out of the control board, put it in here, and then guess what? Sure does make it easy to actually grab one of the legs off of here and then test your wire from there. The great thing about that is you're testing the connector as well as the wire at the same time, and sometimes you can have a bad connector. But anyways, I won't get into that. You have to pay for the class to get all those details, and that's how you would test it. So let's just real quick run a test right here. They should not be connected to each other, and then we'll test it. So in this particular tester, if it goes above 1000, so that'd be 1,000,000 ohms. If it goes above 1,000,000 ohms, then the insulation is good, and that's as good as it's gonna get. Now, if it goes to 0, let's try to get this without causing a spark over here on my, then that's what you would see, okay? Did you see that? All right, and that's typically what you'll see when you plug it up. You'll actually get a Christmas tree light that goes up like that. So in this case, we know that it's working because we got the on light. That means we've got good batteries. And then we know that the conductors are not touching each other or shorted to earth ground because we didn't get a light. Now, one thing I want you to keep in mind is this can hold voltage, so you can actually get a little bit of a shock. You can dissipate this by touching metal, or depending upon how you actually disconnect these, it'll actually dissipate the current itself. But touch these to ground, and that should dissipate the voltage right there. So let's say I got a great insulation on there. I only know how much I see that I can actually test. Again, this could have got damaged by a weed eater, it could have got damaged by anything else. So I'm gonna actually take my LCR, I'm gonna plug it in, and I'll bring it up a little bit closer so you can see it here in a second, but for these purposes, I'm gonna plug it in real quick. And when I do that, it's gonna actually go through inductance, capacitance, and resistance and give me a readout of what it thinks I'm trying to test. So it goes to inductance, and it shows 75.45 microhenries. If my tester has been documented appropriately, which it has, it shows 75 microfarads right here. So I actually wrote that at one point in time because I need to know what it's actually rated at in order to test whether I'm actually getting a good read, okay? Now, how do you do that? This is what's so crucial in the test. It's just like a battery. You need to have the battery tested so you can determine the state of charge at it. So if you go to put a brand new battery in, okay, and it tests at 12.8, you come back out 6 months later, it tests at 12.7, and then you come back out 12 months later, it tests at 12.6, you actually see the decline of the actual, how much charge it'll hold. Now, I have a battery in one of my work trucks, and it tests 12.5 all day long. So in essence, it is a bad battery, and it tests that, and tomorrow I'll go out there and it'll be 11.5. I'll crank it up and it'll start up like that. There's another thing that is important there. It's about buying good quality batteries. But the point being is I knew what it was. We tested every week as part of our regular maintenance on our vehicles. So I knew what it was, and I can check that state as it goes. You need to do the same thing with loops. You need to document the color of the wire, the function that it does, and you need to document the insulation that it tests at. You can do the inductance if you want, but the point of doing the inductance is after the fact, okay? When you turn on a new gate operator and you test that insulation, you know that most likely the insulation hasn't been damaged by a weed eater. You know that most likely the insulation has not been damaged some other way. So you know that you just installed it a couple weeks ago, you know that it looks good, so insulation is just fine. You don't actually need to test inductance. If you do, all the better, because then you can track it as it goes along. Again, just like a battery, you need to know the initial state at what it is, because I have had this happen before. I have tested a loop to be bad, okay, and it still works like a charm. Keeps working, just like a charm, and it never fluctuates up or down, even with different changes in weather, different changes in temperature, and so on. So back to the LCR. This is probably what you were talking about. And a great thing about LCR is this will give you a quality factor. It'll do a couple other things. One of the things that I like, just from test purposes, most of the time I just test this at 1K, and that's fine. But you can change the frequency on it, and you can see how proportional frequency is to the actual test itself. So you can see the difference that you go higher in frequency. As you go higher in frequency, you most likely your impedance changes, and you have, in this case, probably more resistance, and it's affecting the inductance. Now, that's pretty interesting when you look at 100 hertz, 120 hertz, 1K, and then now when we get up into probably what most loop detectors are going to put out in the 60, 70K or something along those lines. So, and this one's a dual display, so you can actually look at resistance and things like that up here up top. But going back to resistance, you can actually test the resistance of this to make sure that you actually have a conductor that's in series. This is deceiving as well too, because you could have a break and show an open on here. That'd be one thing that happened. The other thing that you could actually see is just high DC resistance. You would most likely see that in proportion to an actual insulation test, okay? But that's not necessarily the case, because you could have high resistance, but you could actually not have a damaged spot in the insulation. So sometimes resistance is a good test to have as well too, but DC resistance as opposed to impedance. So Mike, I think that's what we were talking about, was the LCR. That's the other tester that got a little bit of interest when we were having the class, and I would recommend everybody get one of these. You can get a good LCR from X-Tech or Agilent that doesn't have the ESR or as many frequencies, but that's okay. It's just a mathematical calculation to figure out where it needs to be at 60 or 70 or 40 or 50 hertz, which what most loop detectors will put out. And even then, it's not that big of a deal, as you saw with just this test right here. So LCR, this one's the U1733C. The reason why I got this was equivalent series resistance for testing capacitors. Electrolytic capacitors are commonly known, the inexpensive ones commonly known to go bad, and it's real inexpensive to fix in a lot of electronics. So I wanted to know what practical resistance could possibly be in a circuit that had possibly a bad capacitor in there. And the other thing I wanted to bring up, so I know that was probably longer than I needed it to be. It shows 30 minutes here, so hopefully I'll whittle that down to 10 or 15. One of the things that most guys there didn't have, as edge sensors become popular, and sometimes, depending upon the manufacturer that you buy, it comes included with the device, so it may make sense to go ahead and install it. Make sure you get one of these Miller Edge testers. You could talk to Daniel, SAS in Baton Rouge, and they have these things. They can get them for you. And this right here can save your butt, and it's inexpensive. So check that out as well too. So which one are you gonna buy? A very expensive installation tester, a very expensive inductance tester, both, all three? Let me know in the comments.